Hi guys, we are from Group 19 and we will be explaining about the extended Debye-Hückel law. In this video, you will be given the brief intro about the topic and we will move along with the definition and theory, dive into the formula and graph and also its application. But before that, let me introduce to you our group members, which consists of me, Bashira, Sharvina, Praveen, Maisara and Putri Malika. So, what is extended Debye-Hückel law? The extended Debye-Hückel law is one of the approaches to extend the validity of the Debye-Hückel theory. Debye-Hückel limiting law equation gives satisfactory agreement with experimental measurements for low electrolyte concentrations, typically less than 10 to the power of -3 mol per liter. However, deviations from the theory occur at higher concentrations and with electrolytes that produce ions of higher charges, particularly asymmetrical electrolytes. These deviations occur because the model, which is the Debye-Hückel limiting law equation, is oversimplified, so there is little to be gained by making small adjustments to the model.
Alright, now let's dive into the theory of the extended Debye-Hückel limiting law. The theory states that when the ionic strength of a solution is too high for the Debye-Hückel limiting law to be valid, the mean activity coefficient may be estimated from the extended Debye-Hückel law. The formula for the extended Debye-Hückel law is as given above, and my teammate will be explaining it in detail shortly. This expression allows reasonable estimation of the mean activity coefficient for molalities up to approximately 0.1 mol per kg. However, for molalities of 1 mol per kg or more, agreement with the experimental value is very poor. In these solutions, the activity coefficient may actually increase with the ionic strength. Debye-Hückel equation cannot be used in the solutions of surfactants where the presence of micelles, for those who are wondering what micelles are, they are an aggregate of molecules in a colloidal solution like those formed in detergents, and the cross section of micelles look somewhat like this. And the presence of micelles might influence the electrochemical properties of the system.
Hello everyone, I'm Putri Malika. So now I'm going to briefly explain about the formula of the extended Debye-Hückel law. So as you can see, that when the ionic strength of the solution is too high for the limiting law to be valid, the activity coefficient may be estimated from the extended Hückel law. So here's the formula. Log gamma plus minus is equals to minus A times the absolute value of Z plus Z minus times I with the power of 1/2 divided with 1 plus BI with the power of 1/2 plus CI. So you're probably wondering what this word stands for. So here's the explanation of the extended Debye-Hückel law formula. So gamma plus minus, it stands for the mean ionic activity of the coefficient. While for the Z plus and Z minus, it stands for the charge of the electrolyte for the gamma plus minus. However, for Z plus, it stands for the cationic charge, while for Z minus, it stands for the anionic charge. While I stands for the ionic strength, B stands for the adjustable empirical parameter, and C, it stands for the value that is obtained experimentally. For the example of the calculation using this Debye-Hückel law formula, it will be further explained on the next few slides by the next presenter.
So moving on to the application and examples of the extended Debye-Hückel law. In this law, the equation is frequently used to calculate the activity coefficients of chemical species and equilibrium constant at ionic strengths, which are different from those which is used in the experimental evaluation. And also bear in mind that this law is only applicable to an ionic strength, which is denoted by capital I, of maximum 0.01 mol per kg, or also known as molality. In these segments, we also will be looking at the examples and calculation that is applied for this law. As for example 1, calculating the parameter B, the mean activity coefficient of sodium chloride in diluted aqueous solution at 25 degrees Celsius is given, which is the gamma is 0.907 at the concentration of 10.0 millimole per kg. So now estimate the value of B in the extended Debye-Hückel law. So first thing first, we are going to determine the value of ionic strength, which is denoted as capital I. The formula is given on the top left, which is mu equals to half total of the concentration and into the power of the charge. And then now we get the value of ionic strength as 0.01. And from the equation, which is given on the right side of the slide, which is log gamma plus minus equals to A and all that, we substitute the value of all the values given, which is the log gamma is given as 0.907 equals to A. The value of A is given from the table, which is 0.509, and then the charge, and also substitute the value of ionic strength and all that. And finally, we can get the value of B equals to 2.007.
Hi, I am Sarah, and right now we are going to look at the graph involving the extended Debye-Hückel law. Generally, the equation of the Debye-Hückel limiting law is only applicable to an ionic strength of maximum 0.01 molal, that is, only for extremely dilute solutions with very low molalities. Meanwhile, the extended Debye-Hückel law gives agreement with experiment over a wider range of molalities. Here is an example graph of the mean activity coefficient of aqueous hydrochloric acid against its molality. The calculated activity coefficients using the equation of the Debye-Hückel limiting and extended law are plotted together with experimental values. The symbols represent the experimental data. The solid line represents the value estimated using the extended Debye-Hückel law, while the small dotted line is the values obtained using the Debye-Hückel limiting law equation. As can be seen, the values from the Debye-Hückel limiting law can agree with the experimental data only at the very beginning of the curve, which has a molality lower than 0.01. This proves the fact that this law is only applicable to an ionic strength of maximum 0.01. Meanwhile, it is clearly apparent that the calculated mean activity coefficient using the extended law is able to agree with the experimental value up until 0.1 molal. However, the extended law is only applicable at ionic strength up to 0.1 molal. In this figure, we are only going to look at three curves, the red symbols representing the experimental data, the solid line representing the value from the extended law, while the small dotted line being the values obtained from the limiting law. Obviously, the agreement of the Debye-Hückel limiting law can only be seen at the beginning of the curve, which has a molality lower than 0.05. As the Debye-Hückel extended law is only applicable at ionic strength up to 0.1 molal, it can be seen that after the molality of 0.1, the calculated value no longer agrees with the experimental data. This is another example that shows the extended Debye-Hückel law fails at a higher molalities. It has a wider molality range compared to the limiting law, but is limited to agree with the experimental data only until 0.1 molal, and completely disagree with the data at higher ionic strength.
To conclude, we get that the extended Debye-Hückel law is the extension from the Debye-Hückel theory, where it works a little bit better as to slightly higher concentration, which only until 0.1 molal. It is empirical in nature, to even greater concentration for calculating the mean activity coefficient to fit the experimental data. Some other approaches might need to be considered. Hope you get a lot of knowledge from our video, and thank you for watching.